Hey everybody, we're going to do some exponential functions today. I never said this the first time, but hopefully you will pause the recording as you need to copy things down, because obviously it all needs to go into your notes. So I'm not going to stop because I am on a time crunch. I think this is going to go over 15, so you might have to do it in two parts, but we'll see. All right, so exponential functions today. Here's a graph of an exponential function. F of x equals b to the x power. So it's a little bit different because we have x as the exponent. That's what makes it an exponential function. So just be aware of anytime that you have an x as an exponent, that's what's changing. You know, you're going to put in 0, you're going to put in 1, you're going to put in 2. You're going to be basically changing the exponent on this thing multiple times, and then that's what's different, and it's multiplying itself by its base by that number by itself that many times. So what I want to point out in each of these graphs is your y-intercept. All right, so our y-intercept for this guy is 1. So the reason for that is this is the equation y equals 2 to the x. And we're going to kind of use that as our parent function. If you remember, for any of these functions, we've always had a parent function, y equals x. Y equals x squared, y equals x cubed, and so on. So we've always had a parent function that we kind of base things off of. And then our graph grows from there. It either translates, slides up, slides down, reflects something. So all that stuff is going to happen in this situation as well. But our parent function we're going to use as a base 2. The curve of this thing obviously will change depending on what that base is. So, you know, if you're looking, well, let's look at this first. The y-intercept is 1. So whenever you're looking at the y-intercept, your x value is 0 because it's on the y-axis. So it's 2 to the 0 power, which is 1. Anything to the 0 power is 1. So that's going to be 0, 1, which is on that graph. And then if you look at y equals 2 to the first power, my x value is 2, and then when I substitute that in there, I get 2. So my ordered pair is 1, 2. That's also on the graph. And then if I substitute in 2 for my exponent, so 2 to the second power is 4. And then so on. I can do y equals 2 to the third power, and that's 8. Exponential basically just means it's going to shoot up darn fast because whatever you're taking as your base, that's going to multiply by itself, and it's going to keep, in this case, it's going to keep doubling. So if I take 3 times 3 is 9, multiply that by 3 again, I'm at 27. So it's shooting up there pretty fast. So the curve of this thing depends on what your base is, just like before. So if you kind of think parabolas, if we had 5x squared, that got pretty skinny, whereas a 1/5 x squared got kind of wide. Well, that's not going to work the same way here, but as the number gets bigger, it will get sharper as the curve goes. And we'll kind of look at that tomorrow in class. All right, so moving on, let's look at some of the transformations on this. You only need to copy down the red graph here. The blue graph on all of these next slides, that's the parent graph. All right, so this is the graph. This red graph is the graph of y equals 2 to the x plus 1. So the difference in the equation is the plus 1. So what happens here is, this is my parent graph, my blue graph. So if I slide that guy right on top of that, you can see my y-intercept for my blue graph is still at 1, because anything to the 0 power is 1. And then if I add the 1 onto it, anything to the 0 power is still 1, but if I add 1 to it, then it shifts up to 2. So now my y-intercept is 2. So that's exactly what a plus 1 on the end of it is going to shift it vertically. So it's going to change, it's not going to change the graph horizontally at all, but it's going to shift it vertically. So the plus 1 shifts the parent graph up 1 unit. Let's look at another one. Y equals -2 to the x power. Different equation, different graph. So again, you only need to copy down the orange graph here because the blue graph is still my parent graph. All right, so the difference in my equation is that negative in front of the 2. Well, the negative in front of the 2, remember, that's not part of your base. That's like a -1 times 2 to the x power. So all of those things that I just figured out, the 1, the 2, the 4, and then the 8, are all then, once you figure those out, are going to get multiplied by -1. So all that really does is it flips it over the x-axis. So here's my parent graph sliding on top of this guy, and you can see all it does is reflect it over the y-axis, or the x-axis. All right. So my y-intercept here is 1. If I multiply that by -1, I get -1. So that's why it's flipped down. So all those values, the 1, the 2, the 4, and the 8, would all be negatives now. So it flips it down. So instead of going increasing quickly, it's going to be decreasing quickly because it's negative. Very cool stuff. So bottom line is the negative base, the negative in front of the base, reflects the parent graph over your x-axis. All right, one more of these guys. Y equals 2 to the negative x now. All right, so this is very cool, I must say. Your green graph here is now backwards. So it's basically reflected over the y-axis. So if you take your parent graph and slide that on top, it reflects over the y-axis. They both have a y-intercept of 1 still. Your y-intercept is still 1 on both of those. But in this case, because you have the negative x, you actually are, instead of increasing to the right, you're falling to the right. So it's actually decreasing to the right. So as your x values get bigger, your graph is decreasing. Now this is the coolest part about that. Think about what we did just yesterday to fix our negative exponents. If you take that y equals 2 to the negative x power, we would drop down our 2 to the x to make the x positive. Well, what the heck, man? That gives me a base of 1/2. So that means as my bases become fractions, I'm now decreasing. Completely makes sense now, because I'm multiplying by a fractional amount. So I'm getting smaller and smaller and smaller and smaller. That's so cool. You start big on the left, and it falls to the right. All right, so then bottom line is, if you have a negative exponent, that's going to reflect our parent graph around the y-axis. Nice. Okay, so let me give you a couple graphs. Pause it, copy the graph down. We're going to write the equation for this guy. So that basically is our parent graph. No changes as far as directions go. It's rising to the right. You know, it's not doing anything crazy. It's not going down, nothing. But it is shifted. So we're going to have a y equals 2 to the x power. That's our normal parent graph. But instead of having 1 as our y-intercept, we are now going to have 3 as our y-intercept. So it's a shift up of 2. So I have to add a 2 onto that guy. I'm not adding 3 because the 2 is not my y-intercept. It is the shift up from my normal. My normal is at 1, so now I'm shifting up to 3. And that's your equation. All right, let's try another one of those. Okay, very cool. We're now falling to the right. No, we're not. Yes, we are. It's going down rapidly to the right, but it's reflected over the x-axis. So if you remember, reflecting over the x-axis puts the negative in front of my parent. So I'm going to have y equals -2 to the x power. But in addition to that, normally I would be crossing there, and I'm not crossing there anymore. My normal negative graph would cross at -1. So the negative takes care of that part. It gets actually shifted down from the second part, from this -1, down 1, 2, 3 more units down. Okay, so the shifting over the x-axis takes care of the shifting, you know, the negative, the 1 turning into a -1. And then from that point, we are shifting it down 3 more units. You have to kind of be a little bit careful there, because that tripped me up for a little bit. Okay, we can talk a little bit more about that in class if you need to. Very cool stuff. All right, formulas, 2 formulas. Copy that guy down. Nice, easy formula. You've seen it many times. The difference between this formula that you would have done here and then in other classes is it has a plus or minus t on as an exponent. So you can do future with a positive exponent or past with a negative exponent. but your book uses n as the final amount and n sub 0 as the initial amount. In Algebra 1, we used A's and P's. It's up to you. I don't really care what letters you use. As long as you put the stuff in the right place, I am so okay with it. Always remember that your rate is your percent. That percent needs to be changed to a decimal when you use it in a problem. Got to check my time real quick here. 10 minutes. I think I'm going to be good. All right, so here we go. Sorry about that. Okay, so here's this example. The cost of a hamburger is increasing at 9% a year, and it costs $4 now. Project a future cost 5 years from now. So we're going to use that straight formula. Just substitute in what you need to, and then go from there. It's all calculator after that. So our n is going to equal our original amount, which is $4 right now. And then we're going to use 1, and our decision is, do we use a plus sign or a minus sign? Well, prices of hamburgers are increasing. Most of the time, prices don't go down of anything. So we're going to be increasing, so we use a plus sign in there. It's increasing at 9%, so we're going to use 0.09. And then we want to know how much it's going to be in 5 years. So that is the future, so it's going to be 5, a positive 5. All right, so all is well there. Now it's, like I said, all calculator work. So we have to work from the inside out, all order of operations. 1 plus 0.09 is 1.09, and then to the 5th power. You can type that in your calculator just the way you see it, just using a caret for the 5. Or you could take 1.09 to the 5th power and then multiply it by 4. Either way, you should get an approximate cost in 5 years of $6.15 for your hamburger. And there you go. All right. Radioactive isotope decays so that radioactivity decreases by 15% per day. So we're talking decay here, so it's getting smaller. Decreases by 15% per day. We're starting with 40 kilograms, and we want to know how much it is going to have 6 days from now and how much it had 6 days ago. Very cool thing about this formula. You're still using a minus sign in between because it's decreasing, but then your exponent is going to change. When you're doing your future, you're going to have a positive exponent. Past is going to be a negative exponent. All right, so here we go. And equals, we're starting with 40. And then it's going to be 1 minus 0.15. And then it's in 6 days. All right. So we got 40 times 0.85 to the 6th power. Do that all in your calculator, and you should get about 15.1 kilograms in 6 days. Woohoo! All right, exactly the same process for part B, doing 6 days ago, except that we're going to use a -6 for our exponent because it's the past instead of the future. So no Mike Zach, you don't have to write down the 40 times 1 minus 0.15 to the 6th power. Again, you already know that 1 minus 0.15 is 0.85. You guys know that I'm not a killer. You know, I don't want to kill you on the work. I just want you to do the work. So show me stuff that you know, that shows me that you know what you're doing, and I'm all good. So there we go. 40 times 0.85 to the -6th power. Put that in the calculator, and you should get 106.1 kgs. Kilograms. All right, so there we go. All right, I was about to say questions on anything, but you're not here, so you can't ask me. Okay, one more. Let me check my time again. Sorry. Oh, you know what? I'm going to do the second example on part 2. So stay tuned.